Hello everyone and welcome to Live from the Lab. This is the show where we talk about different technologies that Bruker's developed in order to help scientists discover the world around us. Today's topic is single crystal diffraction, specifically a brand new detector technology that we're coming out with. Now this is the fourth generation, that's right, the fourth generation of our detector technology for single crystal diffraction. So we've got a lot of great things to cover today. And to do that, we have one of the experts here in the studio. Before we get over to the studio, what we're going to do is we're going to start with a video.
Structure, function, reactivity. Critical insights to the success of modern science. Insights that can be revealed when looked at in the proper light. Introducing Bruker's most advanced detector yet, the PHOTON IV. Our fourth generation detector features an unparalleled signal-to-noise ratio and higher dynamic range, providing accurate detection for both weak and strong reflections. The PHOTON IV offers the largest active area available in an in-house detector, with no gaps or dead areas. The PHOTON IV's indirect detection design enables true photon counting, ensuring the highest possible quantum efficiency. The high frame rate enables fast readouts and accurate measurements of weak reflections. With the PHOTON IV, not a single photon gets lost. The PHOTON IV single crystal detector from Bruker offers the highest sensitivity for all applications in biological and chemical crystallography, and across all wavelengths including hard radiations such as copper, gallium, molybdenum, silver, and indium. The completely air-cooled design is built to last and comes with a 3-year factory warranty. Unlock a true understanding of structure, function, and reactivity with the new PHOTON IV from Bruker.
All right, we are joined today with Michael Roof. Thanks for joining.
Always glad to be here, John.
All right, and thanks everybody out there for joining us today. So today's topic is going to be this new detector. We just saw that really exciting video.
It's dramatic. It's dramatic.
It is. It is very dramatic. But I think that's reflective of the product itself. Right?
It is. I mean, it's cutting edge. You see, that's actually reflected in the design. When you look at the detector, even that aspect I like, and there's much to like about those detectors. We heard a couple of buzzwords. You know, best quantum efficiency, high sensitivity, large area, no gaps. That's what we will be talking about today.
And photon counting, too.
Yeah.
And this is something that was in the 3 also?
Yes.
Okay.
Yes.
So I think some people may not be familiar with that term, but it's very important for something like single crystal diffraction as photon counting. What do we mean by photon counting?
Photon counting basically means that we are able to detect one single photon when it hits the detector. So we have single photon counting sensitivity. And there's a lot of talk about how this is achieved. There's basically nowadays there's 2 detector technologies, HPCs and then the CPATs, the CMOS pixel area detectors. And they work a little bit differently. If I would have to bring this down to like one sentence, the HPCs, they count electrons in hardware, and then the PHOTON IV counts photons in software. So that's basically the big difference.
And so to be even a little bit less obscure on that, I mean, we're talking the difference between a photon detector and, say, the Eiger line, which is in the XRD products. And I think that's a really important conversation for us to have, because they're both area detectors. They both detect, they're both photon counters, but there's some key differences in that technology which makes one better for one or the other application.
So one of the big differences is that an HPC, the sensor is silicon. So what I have here is just a wafer. It's actually pretty thick. And that's important when we talk about some of the aspects later. These are between 500 micrometers and a millimeter. And the X-ray photons, they are detected in the silicon layer. So you create these electron hole pairs. Then they're pulled by a potential to an anode, a pixelated anode on the bottom of the sensor. And then these electrons are then funneled through indium bump bonds into the CMOS. And there you have then the electrons, and the electronics then apply a threshold, and you basically see a pulse or no pulse. This is how you count photons. I mean, simplified in an HPC. In a Photon IV, that's why I like my show and tell. Engineering probably doesn't like that I handle a big sheet of phosphor. So this is a Gadox phosphor.
Okay.
Gadox oxysulfide phosphor. Those are very, very sensitive phosphors, scintillators, the most sensitive you can get. We control the formulation, we control the thickness, we control the backing. So how they actually work is you have a reflective area.
Yes.
And you have an active area.
Yeah, and I don't know if that comes through on the camera, but definitely this side is glossy, and then this side is more matte.
Yeah. So what happens is the X-rays come into or hit the phosphor actually on the non-active side, because the active side is faced towards the sensor.
Okay.
So what happens then is the phosphorus is very thin. It's only 30 micrometers to 90 micrometers, depending on the radiation.
Yeah.
And then the X-rays, they create like a light pulse, and that radiates in 3D. But it will go in all directions. It will actually go back to the reflector.
Yeah.
And then it will be reflected from there into the sensor. So you basically create like a cone.
I mean, that's really clever. I would have never thought about an intricacy like that, but that really then maximizes the photon efficiency that you're getting out of this thing.
This is how you get a very high quantum efficiency, a very high sensitivity. And because it's a high Z scintillator, those are very, very sensitive to copper radiation, but also to silver. And that is very important. You can imagine that if you have harder radiation, this goes right through the sensor, even if it's a millimeter. I actually did sort of a funny test where I collected a perfectly fine data set with shorter wavelength through a silicon sensor, which just shows if you have an Eiger with a silicon sensor, then most of the X-rays actually go through. And this is why for single crystal, where we cover a wide range, we're much better off with scintillation technology, because we can cover all these different wavelengths.
Yeah, I mean, I think generally when you get to those harder radiations, you're talking like 20% efficiency or so with silicon sensors.
Maybe a little more.
Yeah, 20,
but
30.
With we have optimized scintillators, and those would be then the 90 micrometer scintillators. For silver radiation, we still have 93 percent quantum efficiency.
Yeah, and that's the other game too, is right, the thicker that scintillator becomes, the lower your resolution can become. Right? So you really need to optimize those things.
And that is the same thing is true with the silicon.
Yeah.
So you can imagine if you have a X-rays that come in at an incident angle, make the math simple. When they come in at a 45-degree angle, and you have like a millimeter, you have interaction between the X-rays and the sensor for a very long path. And that that's the diagonal. If it's a millimeter, 45 degree, then basically your other side of the triangle is a millimeter too. So you will smear out that signal over 10 pixels. That's 1 millimeter if you assume you have 100 micrometer pixels. The Eiger has smaller pixels, but you would smear out that signal a lot.
Right. And Now the benefit, because there are benefits, that's why we do use that technology in, say, the Eiger, is you have energy sensitivity. So with the direct conversion technology, where the X-ray photon directly goes into electron hole pair, we can measure the energy of that radiation. And there it's important because an X-ray machine, like Bragg-Brentano, you're typically using a white beam, you're going to get some fluorescence off the sample. So there's a lot of extra radiation going on there. Whereas we're just interested in the one characteristic. So having that ability to separate out the right energy is really important for, say, powder X-ray diffraction.
Yep.
But then for the single crystal experiment, we have a lot of beam conditioning going on to make a nice, fine, perfect beam already.
Yep. So, yeah, in single crystal work, I've never seen an example, actually, where energy discrimination would help. There are some special cases when you have indium, and then because you use gallium also in that metal jet, and then you might have contamination of your indium wavelength with gallium that might cause some problems. There, I would say energy discrimination is needed. But then for a very short wavelength, you would not use a silicon sensor anyway. You would use a cadmium telluride.
And there you can start getting into pretty expensive.
So then you have a very good, very small, and very expensive detector, and that is, not the sweet spot for single crystal work.
Right. Well, and speaking of size, I mean, these detectors are pretty huge.
Yeah.
Even if we think of the small one, that looks like a massive detector.
It's a massive detector. 11 by 7, 11 by 15, rounded. That's very big. That's about 15% larger than the Photon 3. The pixels are also smaller. They're 100 micrometers. The internal readout frequency is higher. It's actually 112 hertz now. And that required quite a bit of work on the software side. We have much stronger frame grabber cards. These are these FPGA cards. They're super powerful. They have a really high data throughput. Kudos to the software developers, because they have to pipe massive amounts of data in a very short period of time through these pipelines. That's really exciting technology.
So with that, maybe it's a good time to switch over to your presentation. So you've put together a few graphics here for us to see what's going on a little bit more in detail.
So just a few slides. I will not spend too much time on that. We probably said most about the new Photon 4 just from a spec point of view. Then, of course, no presentation without data and some structures. And then some more technical details. I also got some interesting tidbits of information out of the developers, which is not easy sometimes. Here's just another glamour shot. We talked about the different sizes, noise-free photon counting, 112 hertz readout. That with a smaller pixel size, with a high sensitivity, that really pushes the technology forward, and it's air-cooled. That's also really important nowadays.
Well, and when you combine then this with a microfocus, you've kind of got the best of both worlds there. You don't have to worry about water.
Exactly.
On either side.
The complete system is air-cooled, and we all know that water is your enemy. When we have system problems, it's very often the algae and not other technology.
And when you get into it, then the water's going here and it's going there, and you can be as careful as you want. You better have a bucket.
So here I have a really short video that just shows you how it's implemented in the instrument. It's a little bit out of focus. It's a video that's taken from a webcam inside an enclosure in Karlsruhe. I think I sped this up by 30. This is a data collection with copper, where you need to go to very high resolution diffraction angles to get to atomic resolution. You see how the detector moves around. It's optimized, and that's also why you see, makes sense now that you have this tapered bezel, because you want to get as close as possible to your incident beam to be able to collect data to about 155 degrees in 2 theta.
And that detector, I don't know if I noticed it in the video, but you can also not only tilt it around, but you can move it back and forward, right?
Yeah, sure.
To get more coverage or more resolution. All right.
And that gets important because we do quite a bit of Poorman's powder diffraction on single crystal. We never, get the resolution you guys get, but we have other advantages. You need very little amount of sample. You get it pretty quick. Here's just some structures I want to show that they did in mostly as development projects. We have this vanadate crystal that we use quite a bit. It's nasty because it has high absorption.
Yeah.
Lead
in there.
It is a very strong diffractor at the same time. So here's just a very small crystal, and here's an image. Really, no background. You see strong, small reflections to high resolution. And then data dump here. I don't want to go too much into this, but what I want to show here is that you can blast this crystal. Basically, you get a good data set in 8 minutes from 1 second exposure times, but then you can push it. You see the last column, that's 20 seconds. And the nice thing is, yes, eventually we'll lose a couple of reflections. Maybe I turn on a pointer here. You lose like 3 reflections, but you significantly improve data. And this is really collected in sensitive mode, photon counting mode with the detector. So that just shows the expanded dynamic range of the detector, especially compared to the Photon 3. That's maybe one of the things I'm most excited about with this detector, the large dynamic range. And then another example that looks a little bit at any parallax at all. Here again, some statistics. The molecule, what I'm looking at here is just the FLAC and the R1. This was really, really a tiny crystal. I will not go back, but these are very small samples. Of course, we have to look at protein samples too. This is from a small lysozyme crystal. It's actually not the best crystal, but diffracts pretty okay with 2 second exposure time. And then what I'm always happy, I'm obviously not a structural biologist. If I see holes in the maps for phenylalanine here.
Yeah, that tells you the resolution.
That always tells me, oh, that's a good structure.
Yeah.
This was a 12-minute data set processed with proteomes. Statistics are from Aimless, CCP4, and a quick refinement from RefMac. Here again, we talked a little bit about that, now a little more technical details. How does photon counting work? HPC detector, we have X-rays hit a pixel, and basically we apply a threshold, and then we get a count. We have a pulse. We have a discriminator threshold. On the CPAT, we call this an event. So we have, the noise is now so low that we can see one single photon as an event, and we call this an event threshold. And then if we see that an event is over that threshold, we know that we see a photon. So the interesting thing now is when you hit somewhere not directly into a pixel, but between pixels, and then you divide up, that charge that you create. In the worst case, all these pulses, they're clearly visible, but they're below the threshold, so you would not see a count at all. And this is where the CPATs, this modern technology, is so exciting because we have what we call interpixel communication. So each of those pixels would not reach the event threshold, but because the pixels are talking to each other. So pixel 4 is talking to pixel 3 and 2. Hey, did you see something? I felt like there was something. And then what we can do in real time is we see, oh, I saw 4, I saw 3, I saw 7, I saw 8. Hey, we're above the threshold. Hey, there was an event. And so we still see.
And then does it use those numbers to be able to kind of like triangulate exactly where that pulse hit then? Like which pixel experienced it?
No, because in the end, we will reduce, when we integrate those intensities, we will reduce those to a point, but that's later done during data integration when we then actually look at multiple frames, determine the profile of a spot, and then try to determine the center of that spot.
Okay.
It's not done on the detector level, but it's then done later on the software level during data processing. And so I still hope that this works. So what did you see on this?
I mean, I see a beam stop. I see, a lot of counts on the outside.
Yep.
I'm sure there's a few counts there on the inside. And,
I have to turn off my pointer. Do you know how to turn off?
Looks like a pretty poor single crystal sample.
Yeah.
I say. Not a lot of spots.
Do you know how
a lot of rings.
Do you know how to turn off a
Well, I would
pointer?
undo what you did.
A pointer? Just on the
Maybe
laser?
you click it again?
Yeah.
There we go.
Oh, here we go. So, yeah. So the point here is that you don't see anything.
Yeah, I mean, I don't even see any like counts in terms of. Sometimes you'll get like gamma ray, or you'll get like a cosmic radiation in there.
There is. We
we
didn't talk about this at all, but we also have high energy event discrimination on that detector. But here the point is, we took a contrast image. It's a foil that has a lot of amorphous scatter. Actually, more than amorphous scatter. You saw some texture there. So we create a pretty strong sort of a flood field, 60 seconds, but we don't have any counts behind the beam stop. That's sort of, people use this as the proof of the pudding, whether you have low noise and
how long was this collective?
That's 60 seconds.
Really?
Yep.
Yeah, I mean, it's one thing when sometimes people show things like that, and it's, for 1 second we collected.
Yeah.
No,
this
2
is
seconds
this
we
is 60
collected it.
seconds.
But 60 seconds.
Yep.
And
then this is something I wanted to show, because there's a lot of engineering going into even little things like how do I determine a point spread function? What is the resolution of the detector? And the field is of course very well defined through the medical imaging, and this is also one of the advantages we didn't talk about. We basically ride the wave of the medical sensors. So that allows us to always have the cutting edge technology, because the development races for medical sensors, so they get better. And we do not have to use or develop proprietary technology for the sensor itself. There's enough engineering in these detectors that we do not, on top of it, want to develop sensors.
Well, and that's a great thing, because then you can kind of harness that tens or hundreds of millions of dollars that's gone into it for the medical application, and now for this, which is, just as important of an application, because knowing these single crystal structures is important. But I mean, this kind of spatial resolution, or this point spread function, this is like one of those conversations that I know, several years ago we always had, because a lot of the technologies suffered from this, where one photon spreads to others. And I think one reservation somebody might have here would be like, oh yeah, you're using a scintillator. Yeah, that's totally going to give you a point spread function, right?
It will give us a point spread function, but the interesting thing, if we go back to the presentation, is there is what they call a knife edge measurement. So you see it in the image that there's basically a very sharp cut with good edges, a lead shield, and then you have 600-second exposures, and then you look at basically this edge here, and then you determine line pairs, and you average these, and then you look at this line spread function, or this edge response function here. So now, when you take the first derivative of that, you get like a Gaussian shape. which is almost like the point spread function, not quite. I don't understand the math completely. But then in the next step, when you take this Gaussian then and you do a Fourier transform, you get something that is called the modulation transfer function. And that's a standard in the imaging technology. And from that, you basically get the information about, how good is the contrast of your system. And this is used to determine the point spread function. And with all the control we have with the scintillators, this is really good now. It's basically slightly better than 1 pixel. So you do not introduce any adverse effects by using a scintillator, but you have all the advantages of being sensitive for shorter wavelength and also being parallax free.
Yeah, and that's one of those where you hit the right number, right? I mean, because if you made that scintillator thinner, if you got rid of that reflective coating on the front, all of these things, it might be able to lower that point spread function even further. But the fact is, once you're under a pixel, you're good. In fact, you're hurting yourself because you're robbing signal.
Yep.
But yeah, I mean, modular transfer function, and that's the same test that we do for our XRMs. Determine can you see a feature or not see a feature, and
I forgot that we're really big into imaging now too.
Yeah, we are. Yeah, Bruker. I mean, we really are. We're turning into a big imaging company.
I'm losing track of what we do. I'm getting too old for this.
The other thing that struck me about your knife edge here is what you had said before with the beam stop, about how there's absolutely no counts on the other side of that knife edge. Yep. And that tells you that the detector itself inherently doesn't have noise.
Yep. So then I got some trivia from the developers. And it's quite impressive that the Photon 4 is reading 180 megapixels per second.
Wow.
So that's 3 times more than the Photon 3. That's also why we had to upgrade the frame grabber that now can handle 6 gigabit per second. That's quite amazing. And then, Ali Aboud, our detector scientist, physicist, the manager of this project. As a good German engineer, they of course had to replace every single part. That's what they did. They did not reuse, I think that's so German, they did not reuse any part of the Photon 3.
Wow.
But the heat sinks are now custom made. The cooling is more robust. My producer said I cannot say robuster. The beryllium window is thinner. The fans are larger and quieter. This is all important because we want to be able to even cool if we're outside, the requirements for the lab. We want to be able to cool these. Then they have now diagnostic sensors that provide smart error reporting, moisture, all kinds of things. It's really marvel of technology. It's really exciting. And this is also why I asked Ali, give me a list of people, and I was actually shocked. You deal with a couple of developers, but there's so many people who are involved. Roger, our great leader, who's also the CTO, who always has the vision, and then of course Ali. Electrical engineering, software engineering, mechanical engineering, of course the application scientists who collect the data, who look at this. It goes on, production engineering planning, service, assembly and testing, marketing. Of course you need the people who buy that stuff.
Yeah.
And then you of course always have these people who just sit around and drink tea and have
the advisory team. I see your name on that part.
Yeah, exactly. That's why I can make fun of those guys. We just have the great ideas and don't have to do the work. I like that.
It would be nice if.
Yeah, exactly.
Could you dig that little photon name a little deeper in there?
Exactly. With that, if you want to have more information, here's a QR code that you can scan. You can watch this great video. Shout out to Video Wisconsin. Mark West does a great job with these, I think. And then you also find the product sheet with specs. And with that, I would like to thank you and would like to thank you for having me.
Yeah.
It's always great fun.
So we're going to get some questions now.
Oh, yeah.
Yeah. So if anybody out there does have questions right now, you can go ahead and type them in on the side of the screen. We will answer them live. Otherwise, we do have a few that came in before. Some of them we may have answered, but we'll see. So the first question is from Linda. Does this work for indium radiation?
Yes.
Indium. Why do we care about indium?
Indium. So the on one end, for lab instrumentation, we have classical copper that we use. And then with the metal jet, we have gallium.
Mm-hmm.
So now we're talking about 9 keV. I get my keVs right. Then we have molybdenum with 17. We have silver with 22. And then you also, in the metal jet, can have a different alloy that has indium radiation. K alpha, and that's 25 keV.
Wow.
So that is really hard.
So that's way up there.
Yep. And again, if you use an HE, we call these scintillators HE scintillator. For silver, you get 95%. So you probably get like 80, 85.
Yep.
For indium, yes, they will work.
Okay.
Because thanks to the high C scintillators.
So if you have that top of the line source, lab source, the metal jet, you can get that top of the line detector to match.
Yep, you get a really nice instrument.
Perfect. All right, so Phil has asked, why have you switched the aspect ratio between the smaller and the bigger?
Oh, that's a good question. So when you look at this detector, and now the smaller detector is now portrait mode. Mm-hmm. You see that.
That's why, because it's the trending thing. You can take portrait mode for social media.
Exactly. You see that there's like this larger part up here.
Yes.
And this is where behind the scenes basically sits some of the readout electronics.
Okay.
And if you imagine if you have this detector in a landscape mode, now if you move it on the goniometer, that means in one direction, you would not be able to collect data to the maximum resolution because you hit the bezel there. And this is why the readout electronics has always to sit on top. And that's just the way it is with these sensors, that the readout electronics sits on the top. And that's why for the large detector, you get the landscape mode and the social media detector, the 8.
That's what we should do.
Yeah,
just call it the social media.
That's an 8. Yeah.
I mean, the other thing too is it's the height, right? So the height is the same.
Yes.
Then, so you don't miss anything. You just have to move the goniometer a little more to capture it.
Exactly. And it's large anyway. I mean, especially when you use these smaller detectors for moly or silver.
Yeah.
You have with the compressed reciprocal space, you get you don't have to move your detector around much. With a smaller detector for moly or for silver.
Right.
Yeah.
All right. From Quinn, can I upgrade from a Photon 100?
Yes.
Photon 100, what is that? First generation?
It's first generation.
Okay.
And yes, you may. There's still a few out there. And we actually have a project right now where I hope we will upgrade some of these to the Photon 4.8. Basically, everything on the D8 Venture, D8 Quest platform, everything back to 2011 can be upgraded. So that's the Photon 100s, the Photon 2s, the Photon 3s. Those can all be upgraded.
So general rule of thumb, if the machine has that new, the design, the Da Vinci design or whatever, the blue sides,
if
the
it
white
has the
front,
same color scheme like the detector, it will fit.
If it has the accordion doors,
no,
we're not doing that one.
Okay. If you see any red in there, or like octagonal shapes in your enclosures, no, those won't work. But you can go back 15 years now, and that's quite a bit of.
And is that about how long the Photon project has been going on? 15 years?
Yes. So the Photon 100 was the first one. That was the size 10 by 10. Then we switched to Photon 2, 3, 4. So.
That really says something too for it, I think, is the refinement of the technology. Because you get to that point now where we can, like you said, you can go in and they're not getting lazy either. They're really reassessing every single component, the heat sink, the electronics, the fans even, They're not just getting lazy and going, use the same fan, use the same whatever. They really thought about every bit of it.
Yep. They're pushing it. Yep.
Yeah, yeah. So it's really ideal, really optimized, and that's great. So we do have a question that came in from Marcos. Hi, Michael. Happy for this new Photon IV detector. Is there some relation to artificial intelligence in the way signal is processed? Regards from Peru.
Yeah, Marcos at in Lima. We do not in the processing itself. There's no AI used, but then we have actually AI projects on the post processing where we look into background determination, where we look at AI being able to detect certain features in imaging itself.
Yeah.
But for the pipeline processing, FPGA processing, I don't think that it lends itself to AI. Yeah, good question, but it's not. We're not that crazy. Ali is not that crazy.
Well, and I think there's a certain amount of thought we always have to put into that. Yes, AI is the new trend. Yes, there's a lot of things that are starting to use that technology more and more. But when we talk about something as consequential as fundamental data, right? Like this detector is collecting your fundamental data that then all other assumptions. And if you publish your data in literature, a lot of thoughts get based on that.
Yeah.
You have to go back and say, this is not something that AI exaggerated, or this is not something that was outside of our scope or our control that led to this. But this is the fact.
Yeah, so we're getting a little bit off topic, but that's basically the ethics of AI. If you have a system and you have rule-based processing and that works really well, there's no real reason to replace that with AI.
Yeah. So, and like you said, in the post-processing, that's where things like that work out really well. All right. And so with that, we've come to the end of our questions and our time. Thank you for joining us, Michael.
Thank you for having me.
Yeah, it's always a pleasure.
Always a pleasure to be here, and hope to be your guest soon again.
Yeah, no, and we're really excited about this. I mean, the detector is such a quintessential part
of
every single crystal diffractometer.
Yes.
So thanks to everybody out there for joining and spending your time with us. So until next time, keep your signal high and your background low.
Happy refining.